2, 1. Let's go. Alright, so we're going to wrap up Chapter 5. And again, you may notice that the title I am using is different from the title of our book. Because I feel like they mislabeled this section, because really it's about eigenvalues and eigenvectors associated with linear mappings. So that's what we're primarily going to talk about. The title of the chapter of the book is Diagonalization for linear mappings, or I think it's just called Diagonalization. Don't really remember. And we're not going to touch that material. We're going to focus more on eigenvalues and eigenvectors. So let's get into it by reminding ourselves of what these things are for matrices. So for an n by n matrix A, an eigenvector is a non-zero vector, so that A times V is lambda times V, where that scalar lambda is called the eigenvalue. So in other words, multiplying by a matrix is the same thing as scaling. So Eigen is stolen from German, and depending on the context, Eigen translates to multiple things, but the one for our purposes is self. So when you read eigenvector, you should be thinking of self-vector, right? Because multiplying the vector by the matrix gives you the same vector itself, just scaled. So in other words, it's either been stretched, compressed, or flipped in the opposite direction, or possibly two of those things. All right. Now, we've talked about these before, and want to remind ourselves again, these are very, very important in the world of matrices for a variety of reasons. So just from a pure algebraic standpoint, it's a very appeasing looking equation. But in terms of practicality and applications, it is probably one of the most significant equations in mathematics. You have probably Googled something today, and the reason Google has become synonymous with search engines on the internet is because they created an algorithm that finds an eigenvector, right? The PageRank algorithm, good stuff. Alright, so how do you find these things? Well, as we noted, you don't really find eigenvectors, you instead find eigenvalues, because eigenvalues, we actually have a very nice turn-the-crank method for computing them. Specifically, you look at the characteristic equation, which is you take your matrix, you subtract a variable off its diagonal, so that can be represented as A minus Ti here, where I is the identity matrix, and then you take the determinant of it, so it's a determinant-valued function, and in fact it's a polynomial, and depending on the size of the matrix, tells you the size of the polynomial. So for an n by n matrix, it's an nth order polynomial. So if we have a 2 by 2, we've got a quadratic. If we have a 3 by 3, we have a cubic, so on and so forth. Fun stuff. All right. Now, since they're the roots of a polynomial, that means there are actually only finitely many eigenvalues. So when we go computing these things, what we do is go to this polynomial, compute its roots. That gives you finitely many eigenvalues to work with. And then for each eigenvalue, you plug that in and then solve for the eigenvectors. Now, today we're going to make that a little bit more formal and a little more precise because we now have linear operators and specifically dimension at our disposal. Right, and so we'll focus a little bit on that. Okay, good stuff. All right, so that being said, we can define these things for operators, and the definition shouldn't be too surprising because given a linear operator, so again, linear operator means a linear mapping on a vector space to itself, so its domain and codomain is the same vector space. A non-zero vector is called a eigenvector for the linear operator if there is a scalar, so that T of V is equal to lambda V, where lambda is called an eigenvalue. Right, so we're literally translating what we saw with matrices in the language of linear operators. Because, again, a matrix induces a linear operator, and vice versa. Every linear operator between finite dimensional vector spaces is a matrix in disguise. All right, cool. Okay, and again, stressing the non-zero-ness of the vector in question, because a zero vector would satisfy this equation for any possible lambda you could choose, so it's not interesting. Okay. So, as I just mentioned, we're basically copying the definition for eigenvector and eigenvalue for matrices, so naturally we want to prove that in the finite dimensional case, this new definition is just the old one in disguise. So specifically, if you've got a finite dimensional vector space, here where the vector space is non-trivial, meaning that the dimension is strictly a positive integer, so dimension 1, 2, and above. Note that we need this to be an assumption because you want non-zero vectors, and if your vector space has dimension 0, the only vectors you have are 0 vectors, so not interesting. Alright, so we got a finite dimensional vector space, non-trivial, a linear operator, a real number lambda, and a matrix representing the linear operator. So again, the representation is using coordinate vectors, right? If you're in a finite dimensional vector space, I can view it as Rn, because it's isomorphic to Rn, as we just proved, and the way we do that is using coordinate vectors with the standard basis. Now, you can use any basis you want for Rn, but the standard one is the one that lets us envision it properly. Okay, so then you're an eigenvalue for the operator if you're an eigenvalue for its matrix that represents it. That's not surprising. All right, but let's actually work out the proof details here. It's not bad. This is a classic, unravel the definitions, and it's good stuff. So let's prove it. All right, so let's say we have an eigenvalue for t. So it's an if and only if, so we have two things to prove. So suppose it's an eigenvalue for the operator. That means there is an element of the vector space, non-zero, so that the equation we want to hold holds. All right. Note that the coordinate vector also must be non-zero, right? If the coordinate vector was 0, that means v, all of its coordinate entries in Rn are all 0, and the only way that happens is if it's the 0 vector. So that's a non-zero vector in Rn, and the equation must be satisfied. Remember, the coordinate transformation is a linear transformation, and in fact, it is a isomorphism, which, not surprising, right? We know that. Well, I don't think we've explicitly stated that just yet, but it should have been clear from how we created it that it's injective and said the fancy one, 1-to-1 and linear, and since we're finite dimensional, it must also be onto, so it's got to be an isomorphism. But anyway, we can pull the lambda in, and boom, there you go. Non-zero vector, lambda is an eigenvalue. Yay! All right, and then that's the forward direction. Reverse direction is basically the exact same proof. Mutatis mutandis. So take an eigenvalue for the matrix. That means we've got a vector that works. That vector can be represented inside of the matrix, inside of the vector space. Right, the coordinate vector, as I just said, the coordinate transformation, as I just said, is onto. So there is something that hits it. It also must be non-zero, and then this has to hold, and the coordinate transformation is 1-to-1, so t of v has to be lambda v. And there we go. Hooray! So there we go. So our new definition of eigenvalue and eigenvector, our new definition of eigenvalue coincides with the old one. Now, eigenvector, right, we'd have to play around with that a little bit more, but we're not going to. We're just going to leave it at that. That eigenvalues basically are the same across the board here. So when we talk about eigenvalues for linear operators, we're truly generalizing what we talked about. For eigenvectors, it gets a little dicier because the elements now are elements of the vector space, but the eigenvalues are always real numbers, so they carry across fine. That being said, we do want to address how eigenvectors are going to behave in vector spaces, and the appropriate way to do that is to look at something we call the eigenspace. So if you have a linear operator and an eigenvalue, you just look at the set of all things that satisfy the equation we want, and that's called the eigenspace. And there's my dank reference for today. So this is from Ant-Man and the Wasp, if you don't know. When I was watching with my wife, the quote is, "Do you guys just put the word quantum in front of everything?" And I burst out laughing at that because anything making fun of physicists, of course, is something that I approve of. But at the same time, I realize that in mathematics, we are guilty of this as well because we just stuff the word eigen in front of everything. So we now have eigenvalues, eigenvectors. We now have the eigenspace. And you pick a math term like there's an eigen equivalent. There are eigenfunctions. I'm sure somebody has something called an eigenderivative. Yeah. So I had a little moment of self-reflection. I was watching that with my wife, and she was like, "That really wasn't that funny of a joke," but I was like laughing hysterically at it for a while. Anyway, so what is the eigenspace exactly? We'll note that it is the set of all things that would be an eigenvector associated with the eigenvalue lambda, but it's worth noting that it does contain the zero vector. So it violates the key ingredient. But anything that's non-zero that's in the set will be a true blue eigenvector, but we want it to be a subspace, hence the name, so it does need the zero vector. So eigenvectors are the non-zero things, the eigenspace is all the non-zero things plus zero. And as I already let the cat out of the bag, this is a subspace of the vector space V, and it's not hard to prove. So the first thing we're going to verify, any subspace needs to be non-empty. Specifically, it has to have the zero vector, and as we noted, the reason we exclude the zero vector as part of the discussion is that it would satisfy this equation for any possible real number. So the fact that lambda is an eigenvalue isn't exactly too crucial to the definition here. All right. So now pick any two things out of the set and any real numbers. If you look at the linear combination, t is linear, so it respects it. But these are coming out of the set, so that means t of v is lambda v, and t of w is lambda w, and then you can pull lambda out of the whole party, and oh hey, there's the input being scaled by lambda. So the linear operator acts as scaling on the input in the same way that the whole reason we did this for matrices, that the matrix multiplication was acting as scaling. So there we go. Yay, it's a subspace. Hooray. Not too difficult of a proof. And in fact, I actually made you prove something similar to this in class, I think, or maybe it was on a quiz. I think it was a quiz, right? I don't remember. I barely know what day it is, so now that we've gone online. Anyway, cool. Well, now that we've got that this is a subspace, and we've got all these exciting new things like basis and dimension that we could talk about, let's apply that stuff to this good material here. So specifically, here's another dumb reference for you up there. So specifically, the dimension of the eigenspace. I gotta drink more coffee. There we go. All right, now I'm jazzed. All right, the dimension of the eigenspace is called its geometric multiplicity. Now, note that if it was an infinite dimensional set, then when we say geometric multiplicity, we got to be a little bit careful. But for most applications that we'll see, the geometric multiplicity will be finite, so we can talk about it. So specifically, right, like if we want to figure out the dimension, you just need a basis. So how do we get one? Well, let's do an explicit example. Let's take the matrix 1, 3, 0, 1. Lambda equals 1 is an eigenvalue. Hopefully it's pretty easy to see that. Anything in its eigenspace, note e sub 1, because the eigenvalue is 1, has to satisfy that equation, which means we've got this matrix equation, and from this we see that, well, v2 has to be 0, but v1 never shows up. So v1 can be whatever we want it to be. So that means every element of the eigenspace can be written as v1 times 1, 0. So in other words, the eigenspace is spanned by the vector 1, 0. So it has a geometric multiplicity of 1. Nice. Pretty cool. So there we go. There's a good, nice taste of what geometric multiplicity is. Now, again, it's worth noting that geometric multiplicity can be defined for any eigenvalue and a linear operator. It's just the dimension of the subspace. Now, it is possible the subspace is infinite, and then in that case, dimension gets dicey because it's not necessarily it's not a number anymore, right? Then you have to start talking about, like, well, is it countable? Is it uncountable? You know, and you have to get into that stuff, so let's not get too far into that. Now, for matrices, there is an analogous multiplicity called algebraic multiplicity. Let's talk about that. So, the algebraic multiplicity of an eigenvalue is the number of factors of that form that appear in the characteristic equation. Now, note, we never talked about a characteristic equation for linear operators. And, in fact, there kind of isn't. I'll leave it at that. So there's something called functional calculus that sort of gives an answer for what a characteristic equation for a linear operator should look like, but that starts going really off the deep end. But it's worth noting that this is something purely that exists only for matrices. For infinite dimensional vector spaces, trying to come up with a characteristic equation is that is a can of worms, let me tell you. But anyway, for matrices, we've got this. Now, let's go back to the matrix we were just talking about. 1301. Its characteristic equation is super easy to see because just set it up. You're doing the determinant of 1 minus t, 3, 0, 1 minus t. So it's 1 minus t quantity squared. And note, we can rewrite that as t squared minus 1. Because squaring doesn't care about the minus sign. So here we see factors of the form t minus 1 actually appear twice. So this is an algebraic multiplicity of 2. Even though it had a geometric multiplicity of 1. Interesting. So in fact, that's actually something that always happens. The geometric multiplicity is always less than the algebraic multiplicity. Your book proves it, if you want to see a proof of it. It's very lengthy, and you really have to, like, go down it's like a complete, like, sidebar that would be, like, multiple slides to get it. Me personally, right, I've looked up proofs of it, and I've read proofs of it, but I never had it proven in a class. I always had it brought up, and specifically I had Professor Fulton, who I've talked about for my, when I took this class. I had him for multiple linear algebra courses, and in every single one, he always stated this, and he never proved it, and he always said, now, you can prove this, but the proof's not very interesting, so I'm not going to do it. And I agree with that statement. I've never seen a proof of this fact that was, like, exciting. That was, like, a good proof. That was like, ooh, that proof's great. It's always a proof that's just like, oh god, this sucks. And the same is true for your book. So I'm going to continue this tradition of always stating this fact and never actually proving it. So if you're interested, see what your book does. They use block matrices to get it. Which is one of the proofs that I've seen of. There's kind of a slick way of doing it by contradiction, because if you assume the geometric multiplicity is bigger than the algebraic, you can, like, show the dimension of your vector space has to be bigger than what it could possibly be. It's like a pigeonhole principle argument. It's kind of a neat proof. So you can work that out if you want. But anyway, so this is always true, and not too surprising. So it turns out that an eigenvalue where the geometric is strictly less than the algebraic is called a defective eigenvalue. And the existence of such things is actually bad news, because it means that diagonalization, which I'm not touching on, can't be done. So, anyway. Alright, so in your problem list, you'll have a fun time with a couple of matrices detecting algebraic and geometric multiplicities. So, and I picked a couple of problems out of the book for you to work on too. So, good stuff. Alright, now I want to wrap things up by explicitly addressing the infinite dimensional case. Because the infinite dimensional case whoa boy, is it exciting. So, as we're about to see, the behavior of eigenvalues is very, very strange. So, right, as I've already mentioned, there's this immediate problem of how do you even find them, right? Because in the finite dimensional case, we can find them by setting up the characteristic equation using determinants. Determinants really require finite dimensions, right, to even define them. So trying to even, like, cook this up in the infinite dimensional case, like, how do you actually get a formula for it? And like I said, there really isn't. But let's see two sort of extreme cases here. Okay, so the vector space we're going to look at is the collection of all functions that have derivatives of all orders. This is called C infinity, and such functions are usually referred to as C infinity functions. So to make this clear, e to the x is a C infinity function because it has infinitely many derivatives. You've got a first, a second, a third, a fourth, and e to the x is really cheap because its derivative is itself. But all your other favorite functions live here, like polynomials are in here, sine and cosine are in here. Stuff that's not in here is something like a square root. Square root function's not differentiable at 0. And there are bizarro functions that have like 5 derivatives and then stop having derivatives. And yeah, those are nightmare things. We don't need to talk about those. If you remember, there is a continuous function that does not have a derivative anywhere. So what you do is you could take that and then just anti-differentiate that. Since it's continuous, it has an antiderivative. And so you anti-differentiate that just multiple times. And so you create these just horrible functions. But anyway. So for this linear space, this vector space, it's not hard to prove that if you've got infinitely many derivatives, so do your scalar multiples and your summations, so it is a vector space. Now, there is a really nice linear operator on this set. Just take its derivative, right? You have derivatives of all orders, so its first derivative has derivatives of all orders. So it is a linear operator, and it's a really bizarre one because every single non-zero real number is an eigenvalue. So remember, in the finite dimensional case, there is only finitely many eigenvalues, and now we've jumped over to the infinite case, and we've immediately found an operator that has not only more than finitely many eigenvalues, it has uncountably many eigenvalues, right? And the reason it's got infinitely many is, well, e to the x is in here, and by the chain rule, the derivative of e to the lambda x is lambda times e to the lambda x. So there you go. Every non-zero real number is an eigenvalue. Oof. So also from calculus, we do know that its eigen space is actually just going to be one-dimensional. It's going to be all the e to the lambdas, right? Because f prime equals lambda e to the lambda f. The only solution to that is e to the lambda x. So it's algebraic. Its geometric multiplicity is actually 1, even though there's like infinitely many of them. Oh boy, it's real silly. Okay, so there's an extreme case where everything ends up being an eigenvalue. What's the other possible extreme? You don't have any eigenvalues at all. Right, now something with that property, well, that's got to be completely insane, right? All right, well, let's let our vector space be C01, the set of continuous functions. The linear operator is the following. Multiply your function by x. Now, note, this is linear, and if you've taken differential equations, this shouldn't surprise you, because I'm multiplying by the independent variable, which is a allowable instance of linearity. And in fact, you can prove this is linear straightforward by feeding in alpha f plus beta f. X distributes accordingly, and it will work out. So multiplying by a function is fine. It won't ruin linearity. What will ruin linearity is if you, like, squared f. So if I multiplied by f, that wouldn't be linear anymore. But multiplying by a fixed function is fine. And if you've seen differential equations, this is not surprising that this ends up being linear. Now, okay, that's totally a linear operator. Let's say you had a eigenvalue. Well, an eigenvalue would mean that there is a non-zero function that satisfies t of f is equal to lambda times f. Okay, so in other words, there is a non-zero continuous function with the property that scaling the function is the same thing as multiplying the function by x, and immediately you should be suspicious and go, there's no function that could possibly do this, right? Because if you think about, in our mind, what does it look like to scale a function, right, and what it means to multiply two functions, right, pictorially that doesn't line up at all, but we can rigorously prove this. Because if we had two inputs so that f of t and f of s were non-zero, well, then this equation would have to hold, and because f of t and f of z are non-zero, that means the eigenvalue has to be those inputs, but that means the set of points so that f of x is non-zero is a singleton. And for a continuous function, that set cannot be a singleton. Right, because then if we think about it, this function is identically zero everywhere except at one point where it's non-zero. Well, intermediate value theorem says that can't happen. So, hey, this has no eigenvalues. So, in the infinite dimensional case, eigenvalues become incredibly difficult to work with. So it turns out that you don't look at what are called eigenvalues. Instead, you look at what's called the spectrum, and that goes all the way off the deep end here. But all right, so I want to wrap up today. So as I promised, we're getting close to the end of the course. I wanted to start talking about some fun things, and here I'm kind of going a little bit off the beaten path, talking about eigenvalues in the infinite dimension case. So eigenvalues are connected to a humongous unsolved problem in mathematics. So let's wrap things up with that. So there's something called the invariant subspace problem, and the question is as follows. If you've got a linear operator, can I find a non-trivial subspace with the property that the image of M under the operator T doesn't escape M? Now note, I want this to be non-trivial because the subspace that consists only of the zero vector, well, T of zero is the zero vector, so trivial satisfies it. And furthermore, if it's non-trivial, it means I need non-zero elements, so my vector space itself needs to be non-trivial as well. So normally you also say a linear operator where the dimension of V is actually greater than 2. If the dimension is 1, then it's easy to prove this because, well, yeah, its output, if it's non-trivial, has to spit it out to non-trivial things, so... But anyway, let's not get too hung up on the assumptions. In fact, if you do look up the formal statement of this, you're going to find there's actually a lot more hypotheses to eliminate trivial cases, but let's just stick with this. So it turns out that this problem is super easy in the finite dimensional case. The answer is always yes, because what you do is just find an eigenspace. An eigenspace trivially has this property, because T of V, well, you're in the eigenspace, so that means T of V satisfies that. So, boom, there you go. You're done. So it's sort of trivially true. Now, it's worth noting here, I'm secretly allowing lambda to be a complex number because, well, as we discussed, the characteristic equation is a polynomial, and sometimes the roots of those are complex numbers. So it's worth noting that this problem is only considered over the complex plane. Over the reals, it becomes a lot more dicey because the dimension for even dimension, the answer is no. Because you don't have access to I if you only restrict your attention to the reals. So we're secretly, like I said, the actual assumptions here are a lot more involved. But for finite dimensional vector spaces, the answer is super easy. It's yes. Eigenvalues are the key ingredient. But, as we just discussed in the infinite dimensional case, eigenvalues don't behave well whatsoever. So, the infinite dimensional case, the story gets very interesting very quickly. So, for a long time, this was a big problem. This was sort of one of the white whales of infinite dimensional linear algebra, was prove this. So, as we noted, vector spaces themselves didn't get formalized until the early 1900s. So, it's not surprising that it very recently was solved. Specifically, the answer ends up being no, and it wasn't until 1976 that it was figured out. So, I wasn't born yet, but close. Relatively speaking. So this is a math result that is approaching its 50th birthday. And it was proven by a mathematician named Per Enflo. In the world of infinite dimensional linear algebra, Per Enflo is he's a god. Basically, he showed up and proved a whole bunch of unsolved problems in kind of rapid succession. So he just showed up and he just annihilated a whole bunch of important problems. So not only did he destroy the invariant subspace problem, he also destroyed something called the basis problem. For that one, he was awarded a live goose as a prize. So if you Google Per Enflo, the autocomplete is Per Enflo, and then the first thing is Per Enflo goose. So check that out. Per Enflo is still with us. He's very old, but he's still around. And doing some great math. Okay, so his example, the infinite dimensional vector space he found where the invariant subspace problem was false, was kind of a convoluted mess of things. So there was still kind of hope that the infinite dimensional vector spaces that didn't have the invariant subspace property were basically pathological weirdo ones. So we can go well, the answer is yes, except for all the goofball infinite dimensional spaces. So there's still some hope that the nice infinite linear, the infinite vector spaces, the nice ones were still good, but unfortunately, that dream was destroyed in 1984, 2 years before I was born, by a mathematician named Charles Reed. So in his thesis, he actually demonstrated that there is a, quote, classical infinite dimensional vector space where things don't work the way you want. So he proved it for what's called the L1 space, which isn't too surprising because even though L1 is a classic infinite dimensional vector space, it's the classic one that has a bunch of problems. So there's two of them, L1 and L infinity. They're the weirdo ones that don't exactly behave the way you want them to. So it's not too surprising that L1 had a problem, but it's really surprising that it took until 1984 to prove it. Now, Charles Reed, I actually had the pleasure of meeting him at a conference in 2011, 3 years before he passed away. He passed away suddenly from a heart attack in 2014, I think, if I remember right. So I actually got to meet him shortly before he left this world. A very interesting guy. And he also got a front row seat to what is without a doubt the single worst talk I ever gave at a conference. So at Bionic Algebras 2011, I gave a talk, and it was absolutely terrible. It was awful. Oh man, it was awful. So he got to witness me just absolutely bombing on stage. So that's great. That is great. That talk was really bad. If you want me to ever regale you with that one, it was so bad. My advisor was in the crowd, and he was audibly groaning and flailing his arms at how bad I was doing. Yeah, that was good. I wasn't making it any better. So, but anyway, so there's my connection to this problem. Now the good news is in other classical infinite dimensional spaces, the answer is yes. So even though there are classic ones where things fall apart, pretty much all of the other ones, all the classically studied infinite dimensional, what the hell is this word right here? Dimensional. Sure, well, I'm going to leave that. Dimensional. I mean, it still reads, I guess. Um, so anyway, in the other classical ones, the answer is actually yes, which isn't surprising, and not surprising that it took a while to get the classical bad ones to screw up. So for other spaces, the answer is yes. And over the years here, the answer has been demonstrated to be yes in other sorts of settings. And in fact, other pathological spaces do have the property, but it still hasn't been fully resolved. And at this point, it's considered the most important open problem in infinite dimensional linear algebra. It still hasn't been solved. In 2012, it felt like it actually got solved. Some heavyweights claimed they had a proof, but almost instantly they retracted it and said, "Oh wait, no, there's a problem," and it ruins the proof. So it's still unsolved. So if you want to get all the PhDs and high fives, go ahead and try to tackle it. Specifically, you need to prove it for separable Hilbert spaces. That's the setting that everyone's pretty sure it's true, but has for some reason resisted all attempts. So, anyway, all right, cool. That's it for today. Have fun. All right, see you next time.